In this video, we're going to discuss about what is Turing Machine, that is called as TM. T for Turing, M for Machine. Myself, Shamila, I'm working as Assistant Professor in Department CSE, RMDEC Engineering College. We're going to discuss about what is a Turing Machine. Before going to the Turing Machine, we're going to discuss about what is the Chomsky hierarchy. In the Chomsky hierarchy, there is a hierarchical representation of language that are accepted by a different machines. For example, there are four types of Chomsky hierarchy: type 0, type 1, type 2, type 3. Type 0 is called as unrestricted grammar, and then type 1 is called as context sensitive grammar, type 2 is called as context free grammar, type 3 is a regular grammar. In the type 0, that belongs to the recursive enumerable. Then type 1 is a context sensitive, type 2 is a context free grammar, type 3 is a regular grammar. So it is what we called it as a regular grammar is called as a finite automata, non-finite automata, and that particular grammar is called as type 3. The type 2 is called as push down automata, PDA. Example, PDA. Type 3, type 1 is called as grammar which belongs to context sensitive grammar. Type 0 is the grammar which belongs to recursive enumerable. Recursive enumerable means it's a Turing machine, it's automatic acceptor. For example, automatic acceptor, automatic micro oven, fridges, automatic on off. That machine comes under the Turing machine. So two major model of automata: generator, acceptor. Generator is a output and without input. With output and without input, tell us how to generate all the strings in the language. Acceptor, with the input and without output, tell us specific string in the language L. So here the generator is with output and without input. Acceptor is with input and without output. So here the schematic diagram for the finite automata is represented here. That is a finite control. The finite control is moving from left to right. For example, input is A, B, A, B. So it will read the amount of information from the leftmost cell and move to the next, like that it will move towards the right. So left side it should move, is again it should go right, like that. That tape head will be moving from left to right, both the direction, bi-directional it will move. The control represent the state and transition function. The tape contains input string. The arrow represent input head. The pointing at the next input symbol to read the next input. So here what is that pointer is, it points towards like arrow mark, it read that input, and if you move to next means it move next. So like that it will move from left to right and right to left. That is the representation of the tape. So next we are discussing about that push down automata. Input string same as FSM, cannot be backup, finite control, it have a read it, pop it and ignore. Push and ignore is done in the stack operation. Here finite control have the stack operation. If you want to push inside a stack, we can push from the topmost layer of the stack. How the stack works, the whatever we are inserting in the first, it will go at the bottom, or next it will go up, next it will be above. So what we have inserted last, it will be above, like biscuit packet. That is a stack structure, correct? So like that the finite automata will work. The finite automata is unlimited unrestricted memory. It have a similar to finite automata, but it have a unrestricted unlimited memory. The Turing machine have a infinite tape, unlimited memory. The tape head can read, write the symbol, move around on the tape. It will read from left to right and right to left. It will write the information, read from the machine, move back towards the over the initial state, like that. It can be doing it process in the tape head. The output is accept or reject, either two states. One is maybe accept, another state is reject. Turing machine can do everything in that real computer can do. Whatever the real computer will do, the Turing machine also will do the same computation limits. The Turing machine have a read it, write it, tape as infinite memory, the specific state of rejection, accepting, and then symbol representation, the blank symbol. So the blank symbol is represented as tau or B blank for B. So the Turing machine can both write on the tape as well as read from it. The Turing machine have the seven tuples. Those are Q, sigma, tau, del, Q naught, Q accept, Q reject. Q is a set of states. Sigma is a set of input alphabet containing blank symbols. And then tau is a tape element. Whatever the tape element present in the stack, that is comes under the tau. Del is a transition from one state to another state where it moves. That is a del transition. Either right side or right side is represented as L, or L for left or for right. And then Q naught is a start state. It represented using arrow mark. Q accept means it's the final state. The condition is accepted. Q reject also a final state, but the condition is rejected. Maybe a Q accept or Q reject, you will get an output. The outcome is accept, reject, or loop. So there is a three outcome. Maybe it will accept, maybe it will reject, maybe it will loop. So the Turing machine have seven tuples: Q, sigma, tau, del, Q naught, and Q accept and Q reject. So next we're going to discuss what is the mechanism behind this Turing machine. With the head is over on the tape square containing a symbol A. See this here? Here the symbol of the tape first initially have A. We are moving the tape symbol A to the next to the B, one step left. Left means you should represent L. L. Okay. The third component in the either L or R can indicate whether it moved to left or right after writing. So either left or right movement replacing that movement is written in the last third symbol. Here they have discussed a formal definition for the given diagram Turing machine. Q is as a finite states Q0, Q1, Q2, Q3, Q4. There is a totally five states in the given transition diagram. Input transition is 0, comma 1, that is sigma. Del transition, they have a tau symbol, stack symbol is 0, 1, X, Y, and blank symbol B. So here the stack contains the element is 0, 1, X, Y, tau. So Del describes the following transition table. Like for the given diagram, if you give Q naught, it will be moving to the Q naught. If you're giving 0, it will move to the right. It will read the Q1. If it is 1 means it will not do any action. So you can represent null action, null. So hyphen. X also no action. Y, if it is a Y, it will move to the right and go to the what state? It is Q Q3 state. So is represented as Q3YR. Q accept is here is Q4 because it's a double circled. Q reject is nothing. So in this video, what we have discussed is what is Turing machine, and we have discussed what are the tuples of Turing machine, and we discussed about Chomsky hierarchy, that is type 0, type 1, type 2, type 3, and then seven tuples of Turing machine, and one simple example for Turing machine. We'll see in the next video how to draw a diagram for a Turing machine. Thank you.